Okay, let's get started. So last time I ran out of time with about 5 minutes of important material left to cover, so I just want to, I sent email about that, but I want to get it into the record so that you all have it in case it's important later. So if you remember, last time we sort of looked at blocking flows as a technique for finding max flow. We argued that a sequence of n blocking flows was sufficient to find a max flow. And then we began to analyze the time for blocking flows by breaking the blocking flow algorithm into this set of 3 steps: the advance along an edge that still has residual capacity in the admissible graph, a retreat along an edge that you've decided cannot reach the sink, and then taking an augmentation through a path that you found from the source to the sink, right? And we argued that in order to analyze the time of the blocking flow, we just needed to analyze the time of these 3 pieces, and immediately decided we could ignore the advance steps, because every advance through an edge is followed either by a retreat through that edge or else by an augmentation through that edge. And therefore, if we just look at the retreat and augment times, that will also cover the advance time. Now, the retreat time was very straightforward, because when you retreat along an edge, you destroy the edge, and you never visit it again in a particular blocking flow phase. And that bounds the total retreat work by order m, very straightforward. So really what remains is to bound the augmentation work. And there are a couple of different ways to do this that produce different bounds for a blocking flow calculation, and therefore for a maximum flow calculation. Now, the simplest observation is that an augmentation takes n time at worst, because the path you're augmenting on involves n edges, right? So this is sort of analysis 1, is that it takes n time, because that's the length of the path that you're augmenting on. And it destroys one edge, because it saturates it. So it saturates one edge in the admissible graph. And this implies that the total work of augmentations is how much? Nm, right? If you just charge the work to the edge where you are, to the edge that gets destroyed. Okay, so that tells us that a blocking flow calculation, the retreats are totally dominated by the augmentations, which take a total of nm work, and that implies that you're going to find a max flow in order mn squared time, right? So notice that this is still better than shortest augmenting path, right? Which was order m squared n, right? So the blocking flow technique does somewhat better than the shortest augmenting path technique. Where is it achieving its savings? How is it doing less work at a high level? Yeah?
It's not redoing the work of starting from the beginning each time, looking at all the shortest paths.
Exactly. In shortest augmenting path, you do a full m work just to find one augmenting path and saturate it, right? In a sense, the blocking flow algorithm reduces that m work of finding an augmenting path and saturating it to n work to saturate the augmenting path, because the finding is now spread out over all of the different augmenting paths that you find in the admissible graph during a blocking flow calculation. So blocking flow spreads out a bunch of the work and really gets the main work down to n per augmenting path instead of m per augmenting path. Now, those of you who went to the Friday optional lecture about push relabel probably saw a similar bound, because push relabel is another way to kind of spread out this, this global work and really focus the work down on just doing the augmentations. Right? Push relabel does it by not looking for a whole path at once, but instead just kind of moving flow around a little bit at a time. Okay, good. So we had this bound, which is a strongly polynomial bound, which beats shortest augmenting paths. Right? Now the second analysis, instead of instead of bounding the augmentation work by charging to an edge, bounds the augmentation work essentially by charging to the value of the flow. Okay, so the point is that an augmentation through this graph adds at least 1 unit of flow to whatever flow it is that you're building, right? Blocking flows are augmenting path algorithms. They keep adding flow, right? And so as they add flow, they never remove. And so we can conclude that the total work of doing the augmentations, right, is order n times f, because for each unit of flow, you're doing at most n work. Okay. And what's interesting about this order nf bound for augmenting the flow is that this applies over all the blocking flow steps. Right? You know, I find some flow in the first layer graph when I'm looking at distance 1. I find some more flow at the second layer graph where I'm looking at distance 2. And I keep on finding more flow. But all of this flow together contributes to the total max flow that I'm finding in the graph. And so it's not just order nf over a single blocking step. It's order nf over all of the n blocking steps that you might perform as you're finding the max flow. Does that make sense? Okay. And so that implies that we find a max flow in order, well, nf for the augments, and how much work are we doing for the retreats? Mn, because there are n blocking phases and we do m in each. So we have order mf plus nf, order mn plus nf, which we can write as order n times m plus f. Okay. And here again, we have something that is better than naive augmenting paths, because in naive augmenting paths, the f was multiplying in m, where you are sort of spending a whole graph search for each unit of flow. And instead, we now are able to get that with an n multiplier instead of an m multiplier. Okay. Now, this by itself is kind of nice. I mean, for unit capacity graphs, it can give you a slightly better time bound when the flow is very large. But where it really gets interesting is in scaling. Right? So we talked about scaling, about rolling in 1 bit of the capacity measures at a time. And the key observation that we made when we scale is that the new bit creates a max flow problem with f equal to m. Does anybody remember why, if I scale in 1 bit, the max flow in the resulting graph is at most m? Right, we use this argument in our analysis of standard augmenting path scaling. And we're just going to reuse it here. Yes?
Your min cut has most n edges to it.
Right. So the key is that before the scaling, you've got some min cut, which is saturated. Right? In other words, it has 0 additional capacity. So all of the edges crossing that cut are at 0 capacity before the scaling step. So when you bring in a bit, each of them gains capacity at most 1. Okay, so you have 1 unit of capacity on each edge crossing the cut. There are at most m edges crossing the cut, and therefore you have a total of m capacity on that cut, which proves that the max flow value is at most m thanks to max flow min cut. So that's just a restatement of what we've used before. So if a new bit creates max flow with flow value equal to m, then our blocking flow analysis, number 2, says that the time to find a max flow in that new graph, and you just plug in f equals m over here, is order mn, right? And that means that the scaling time bound for finding a max flow is order nm log of u, okay, or actually mu. Okay. So we get a really nice, we get a better strongly polynomial bound than we got from standard augmenting paths, and we get a better scaling bound than we got from augmenting paths. Now, this is not the end of the story for max flow. We could say, is it possible to have everything? So you'll notice that the scaling bound is better than the strongly polynomial bound, right? The scaling bound looks kind of like nm, as opposed to the strongly polynomial bound of n squared m, right? So do we have to sacrifice a factor of n in order to get a strongly polynomial bound? The answer is no. So I won't call this an analysis, but technique number 3 is to use a clever data structure. Okay, so if you think about our advanced retreat block analysis that we did up there, there's a feeling that we're not doing it as cleverly as we could. Like, why is it that after we have, finished this whole advance, we found the sink, we now know there's just one edge that's going to be saturated? Why do we have to invest n work in actually walking through the augmenting path, updating all of the capacities, and saying, oh yes, this is the edge that gets saturated, let's remove it from the residual graph? So if we try to sort of abstract away the operations that are needed on the admissible graph in order to support these advanced retreat and block steps, we need a clever data structure that can do the following things. Maintain a directed tree of positive capacity edges. So essentially, we're going to keep track of various edges that we have identified as having, forest. So we're going to keep around a forest of trees that have positive capacity edges on them, okay, where we've already discovered this, and we don't want to waste time discovering it again. And we are going to implement advanced retreat and augment using these trees. The way we're going to do it is with the following operations on these trees. So the tree operations are what we'll call advance to root, or find root. So this is saying if you're on any vertex at all, we want in a single step to jump to the root of the tree of capacity, of edges that have capacity that come out of that vertex. Okay. Once we do advance to a root, so skipping all of the advances that we already did in the past, we're then going to ask, okay, let me find another edge that's coming out of the root that I have found, and that will take me to another tree. Okay. And if I discover that this edge has capacity, then in fact, I've got a much longer path that continues from my first tree on through the second tree to its root. And so what I'm going to do is link these two trees together, saying I've discovered a capacitated edge, and now I have a bigger tree of capacitated edges. Okay. When I get to when I do a find root and I discover that I have found root t, then that will tell me that I have advanced all the way on a path to the vertex t. Okay? And that's going to make me happy because somewhere in the leaves of my tree will be s. And so I will now augment along this tree, which is I will decrease every capacity of an edge on the path from s to t on these trees. Okay. By the minimum capacity on the edge, on the path. And then finally, I'm going to need the operation of cutting, because when I do this augmentation, I will saturate some edge on the path. And this is where I save my work, right? When I saturate an edge on the path, really, that only destroys one edge. So I'm going to keep all of the other edges around and say they still have capacity. And so that's going to break my tree or my path into pieces. But the pieces are still pieces with capacity. And so I can use them again when I start again from S and advance to the current root of S, S's tree, and then look for another tree to link to it. So if you can support these four operations, advance, link, augment, and cut, then you can use that in a blocking flow algorithm. Yes?
Do you not augment that edge then that was between the two trees?
Well, you do in the sense that this edge that you cut did have capacity before the augmentation. And the amount of augmentation that you do is equal to that capacity. In other words, you subtract that capacity from every edge on the path. And that brings the capacity of this edge to 0.
What about the edge before that you drew in? Yeah.
Oh, yes, that also gets augmented, right? Because you found that that edge had capacity, and you added it to create this path. And so it gets its capacity decreased just like every other edge on the path. Okay? So it's this weird data structure for sort of taking trees, putting them together, breaking them apart, and whatever the current state of the tree is, being able to jump to the root of the tree and also instantaneously find the minimum number on a path to the tree, on a path from a leaf to the root. Pretty bizarre collection of operations. Oddly enough, this turns out to be useful in quite a few different algorithms. Okay? And so somebody noticed this and invented a data structure for it. Who do you suppose it was? Indeed. So Slater-Tarjan developed something that they cleverly called link-cut trees, which support all of these operations in order log n time. Even better, they do it using splay trees. Okay. So you decompose, the way you represent these trees by basically creating different trees that are put into the splay tree. It's a fascinating data structure, and of course their paper about it is quite nice. I unfortunately don't have a full lecture to give to it, so I can just point you at it as a pretty cool data structure and say you get this nice bound for operations. Now what's great about this is that if you look at the way we described our blocking flow algorithm, since augmentation now takes order log n time, okay, that completely drops the cost of doing a blocking flow algorithm. Okay, so with these link cut trees, you can do a blocking flow in order m log n time. Okay. Right, because now you charge the cost of the augmentation to an edge, but the augmentation cost is only log n. So you get an m log n time bound. And so that means that you can find a max flow in order mn log n time. Pretty much as good as the scaling bound, but with a strong polynomiality. Yes.
Is that O log n amortized?
Well, yes. Sorry. The link cut tree, as you might expect, since it's based on a splay tree, is an amortized bound. But since you're using it in a max flow algorithm, you're right, all of that gets put together into the bound for max flow, and so the fact that it's amortized doesn't matter, because this is a worst case bound for max flow, because all the amortization happens while you're computing the max flow. Okay? So that's great. Some tweaks by Goldberg and Tarjan improved this to order mn log base m over n of n. Okay? So when m is large, this term goes away, and you're left with order mn. For a very long time, mn was it. You couldn't do there seemed to be this mn lower bound that we were kind of fighting, and nobody could figure out how to get past it. Okay. Back in the late 90s, Goldberg and Rao took the next step. And so this remains the best strongly polynomial bound known. But Goldberg and Rao, sorry, that's not quite true, took the next step and gave a bound. So you remember last time we proved specialized bounds for graphs with unit capacity edges, and you're doing some more of them in your homework. So in class we proved m to the 3/2, and in your homework you're proving mn to the 2/3 and m root n, if I remember what I put on it. So that was for unit graphs. Goldberg and Rao showed that you could apply scaling techniques to these graphs with unit capacity edges, and achieved bounds of m to the 3/2 log u and mn to the 2/3 log u. So after a long time where scaling didn't help you in terms of your time bound, Goldberg and Rao brought things back to a place where now we have scaling bounds that are better than the best bounds we can achieve using strongly polynomial techniques. Orlin, just a couple of years ago, used this scaling methodology to finally get rid of the log in the strongly polynomial time bounds. Essentially, he uses scaling when he forces u to be small and then applies the scaling techniques. And so once u is small, you can get these bounds, and it doesn't impact the overall mn time bound. Okay? And so this is sort of the state of the art on exact algorithms for max flow. That you can do order mn. We still haven't been able to beat that bound strongly polynomial in a strongly polynomial bound. We have scaling algorithms. They're very clever scaling algorithms. You can't just apply scaling. There's some really new ideas in here that sort of achieve the special bounds that were previously only known for unit capacity graphs. And there remains this huge open question: is it possible to beat mn in a strongly polynomial bound? We don't know. However, just to finish telling the story, that's the story for exact algorithms, but there's also been a lot of progress on approximation algorithms. Actually, before I go there, let me say, in practice. Okay, so these are theoretical bounds. What's going on in practice? In practice, max flow is easy. So if you can reduce your problem to max flow, you're in really great shape. Andrew Goldberg has done a lot of experimental work on max flow algorithms and variants thereof. And he essentially claims that if you use push relabel, which is the algorithm that Jin and Ophir presented on Friday, if you use push relabel plus some clever heuristics that are pretty common in practice, plus random ordering of edge lists, then you pretty much always get a time bound that looks like order m log n. Not a provable one, but sort of experimentally, you get pretty close to linear scaling in the time for max flow. So it's a great idea to transform your problem into a max flow problem if you can. because there are these very powerful and effective algorithms for solving it in practice. Okay. So now, approximation is kind of the new hot thing for flows. We started some of this many years ago looking at approximate max flows in undirected graphs. It turns out that you can do better on them. But the work that I was involved with has long since been overtaken by many other people here at MIT, actually, some of whom were in this class just a couple of years ago. The latest state of things is, roughly speaking, that you can find a 1 minus epsilon approximate max flow. So it's within epsilon of being the maximum flow, but is not quite a maximum flow, in m to the 1 plus little order of 1 time. So they're converging on linear time. So what this means is it's m to the 1 plus something that gets arbitrarily close to 0 as m grows. So it's converging to linear time. And that's really exciting. Unfortunately, from my perspective, this is using linear algebra, which I hate. So I've kind of fallen off of this particular train. They're using techniques that are, that are distasteful to me. And so I'm really hoping, and they're distasteful to me not just because I dislike linear algebra, but because it feels like they're invoking something which shouldn't have to be invoked. Like max flow is a beautiful combinatorial problem, right? And to have to start talking about numerical analysis, linear system solvers, and things like that just doesn't make sense to me in a problem that's really about finding paths through a network. And so it's my hope that someday we'll have a combinatorial linear time exact algorithm. And hopefully one of you will be the person who does it so that I can take a little bit of credit for having made it happen, okay? So there's lots of opportunities to sort of extend this work, either in that horrible linear algebra or using more combinatorial techniques, okay? So that's all I have time to tell you about max flow. Are there any questions before we move on to our next topic? No? OK. So we're not moving too far afield. We're going to take max flow and we're going to add another layer of complexity to it. And we're going to answer that really burning question, why didn't I use C for capacity? Okay? Which I'm sure has been distracting all of you for the past couple of lectures. Okay? So we've looked at max flow, which is the problem of getting material from here to there, while being feasible, getting as much material as possible from here to there while maintaining feasibility of capacities. But we've seen there can be more than one max flow, right? How do we distinguish among them? Maybe one max flow is better than another. Well, we're going to be looking at a particular differentiator here by talking about min-cost max flow. So we take our standard max flow problem, but we add a cost C of E on every edge E. Aha! This is why I had to reserve C. Okay. Now you might ask why we don't just call them prices and use P so that I could free up C for capacity. The problem is that we use prices later for something else, so P isn't available either. Okay. Okay. And our goal now is to find a max ST flow, minimizing, let's call it F, minimizing the sum of edge cost times flow through edge. Okay. The total cost of the flow. Now, what's important to notice here is that this is a per unit cost. So if I send twice as much flow through an edge, it costs me twice as much. This is very different from a model in which you would say, well, you can buy this, right? You can buy this edge, and then you can send flow up to its capacity. Okay, that's not what we're studying, which is a good thing because that's NP hard. Okay, and so we are instead just looking at this per unit flow cost. Right? Oh no, so this is still a max flow problem. We are simply adding this on top of everything we've said previously about max flow. So it has to be a flow, it has to be it has conservation, it has to obey the capacity constraints, and so forth. But now we're additionally looking at its cost. Okay. Important note, costs can be negative. What does it mean to have a negative cost? Well, it just means that you have a profit for sending flow through an edge. Okay. And we'll sort of explore that as we proceed. Okay. Now here's another thing to note. Pushing flow on it through an edge, since we're talking about max flow, creates a residual edge, right? Let's push through edge. So it creates a residual edge, E reversed. No, let me not introduce more notation. Let's just call this edge UV, and this creates a residual edge from V to U. Right? That's because we're talking about flow. But what should its cost be? Right? Now that we've defined a cost on the forward edge, we've got to decide what the cost is going to be on the reverse edge. So what should it be?
Minus of C.
Right. So we set the cost equal to minus the cost of the edge from U to V. Why is that the only sensible thing to do?
So you have it cancel out if you send the flow there and then back.
Exactly. What this means is that if I send a unit of flow forward on an edge of cost C of UV, that costs me C of UV. So if I now use the residual arc to send a unit of flow backwards, that has to be equivalent to removing the unit of flow that I originally sent. So if it cost me C of UV to send the flow, then I have to recover C of UV by unsending the flow. And so we represent that with a cost of minus C of UV, which of course will be negative if the original cost was positive. In other words, when we push through an edge that has positive cost, we create a residual edge with profit on it. Okay. All right. What next? So there's a variant. So before, max flow was pretty much the obvious optimization criterion, right? Send as much flow as possible. There's a natural variant here where we just want to find the min cost to send some amount V units of flow. Now that we have another measure of the flow, namely its cost, we can now decide to fix the amount of flow that we want to send and just ask about sending it at minimum cost. Okay? But it's simple to solve this problem if we have a solution to the general min cost max flow problem. So if you had a solution to this problem and you wanted to solve this one, how would you do it? Yes?
Create a new sink at the end that connects the previous sink with capacity B.
Exactly. You would take your original graph with its S and its T, and now you would just create a bottleneck. This is sort of like the fixed demands problems that we looked at before. You could create it either from S or from T, but the key is that you give it capacity V. So the max flow in this new graph is V, and now you can find a min-cost max flow in this graph. Okay. Now, clearly this problem generalizes max flow because it is stated as a generalization of max flow. However, I will argue that it also generalizes shortest path. So suppose that I tell you, here's my graph, unit capacities. I want to send 1 unit of flow from S to T. What's the cheapest way to send 1 unit of flow from S to T? Yeah.
You just assign the cost of one to every edge and say you want the
I don't know. So I'm saying I have a graph with costs, right? I'm given a graph with costs, and now I'm told, we'll find the cheapest way to send 1 unit of flow, right? It's this problem, the variant, where I'm specifying V. I'm saying it's 1 unit. How do I solve that problem optimally? Yes?
Is it like the same problem where like the cost of the edge lengths?
Too much work. Right? That's my point. If I just want to send 1 unit of flow and the capacities are all 1, I don't need to solve a Maxwell problem. I claim that the best way to send 1 unit of stuff from S to T is to send it, that is the cheapest way to send 1 unit of stuff from S to T, is to send it on a shortest path, according to the cost metric, right? So cheapest way to send 1 unit from S to T on unit capacity edges is to send that unit on a shortest path. Where our metric is the edge costs, C of E. Okay. Is that clear? Okay. So now we're going to try and solve this problem. And we're going to take the same approach as we did last time. Before we get into algorithms, let's figure out the structural aspects of this problem. Okay. So if we're thinking about structure, what was the first thing that we did thinking about structure for max flow? Well, it was path decomposition. Right? Because min-cost flow is a flow problem. You're finding a flow. So you can decompose any flow decomposes into paths and cycles, right? So any flow is a sum of paths and cycles. And it's worth stating that the cost of the flow is equal to the sum of the costs of the paths or cycles times the capacity of the paths and cycles. Right? So I can take this flow and say this flow consists of 2 units traveling on this path, 1 unit traveling on this path, and 3 units going in this cycle. And I can compute the cost of the flow by looking at the cost of that path, of the first path, multiplying it by 2, the cost of the second path, multiplying it by 1, and the cost of the cycle, and multiplying it by 3. And that gives me the overall cost of the flow. Okay? Good. So that actually, since we're going to be doing some scaling, this lets us bound. Let's not do that yet. So let me tell you about one other variant, one other problem variant, which becomes interesting now that we're doing min-cost flow. And that is the problem of min-cost circulation. Okay. So I mentioned circulations before, right? A circulation is equal to a flow with balance everywhere. So there's no longer a special vertex S and T where you have flow leaving S not balanced and arriving at T not balanced. Instead, you just have flow, you have balance at every single vertex, but you might have non-zero flow on edges as long as the total balances. Okay. Now, circulations, when you are talking about max flow, aren't really interesting, right? So what would a max circulation be, right? I mean, you can talk about feasible circulations, but the circulation of 0 is a feasible circulation for any problem without lower bounds, and so it's sort of not interesting. But once you put costs on the edges, then it becomes interesting to talk about min-cost circulations. Why is this problem no longer trivial once you have costs on the edges? It's because of these negative edges, right? You can put negative costs on edges, and so you get money by sending flow on those edges. And so the minimum cost circulation problem is then really asking, let's try to collect as much money as possible by sending flow on negative cost edges. The problem is that we have to preserve balance while we do that. So there may be some negative edges that we can't use because it's too expensive or impossible for us to rebalance the flow when we send flow on those negative cost edges. Okay? So that's the min-cost flow problem, min-cost circulation problem. And actually, min-cost circulation is a more elegant problem than max flow because there's no longer this special S&T pair, right? So if we had costs in the beginning, it would actually have been more natural to think about the min-cost circulation problem, okay, because it's cleaner. And one way it's cleaner is that you have a cleaner decomposition argument. So what could we say about the decomposition of a min-cost circulation? Yes?
It should be made up of random cycles.
Right. So any circulation can be decomposed into, at most, m cycles. We no longer need to think about paths at all, right? But the argument is the same, and the bound on the number of cycles being m is the same, right? As you do the decomposition, each time you find a cycle, you can take an edge out of the graph. And so you end up with, at most, m cycles. Okay? Now, is this problem, I mean, this problem seems pretty closely related to min-cost max flow, but we need to prove the relationship. Okay? We need to give some reductions. So let's start with a reduction in one direction. So reduction 2 min-cost max flow. So suppose that you had a black box that could solve a min-cost max flow problem. Okay? And you're told to come up with an algorithm for min-cost circulation. Okay? So here's my graph G, and I'm supposed to find a min-cost circulation in it, and all I have is a black box for min-cost max flow. How could I solve my problem? This is one of those annoying answers where the answer feels like you're cheating. Okay. Yes?
You just take some S&T off the side.
Good. So here's S, here's T. Solve the min-cost max flow problem. Okay? Why does that work? Does it work? Yeah, it's cheating, isn't it? I mean, it's kind of annoying, but formally it fulfills all of the necessary requirements, right? What's going to happen when you try to solve a min-cost max flow over here? Well, the value of the max flow is going to be 0, right? There is no flow from S to T, but it has to be min-cost, right? And in order to make it min-cost, you're going to send lots of cycles of flow around in G as necessary to minimize the cost of what you've got. All right, so that was the easy direction. Let's look at a reduction from min-cost max flow. Or actually, I should say that this is generally abbreviated as MCF, min-cost flow. And it's taken for granted that you're looking for a min-cost max flow. Okay? So now, let's suppose that we have an algorithm for min-cost circulation, and we want to solve min-cost flow. Good. So now we're given this graph G. Okay. And we want to find a min-cost max flow from S to T. But our min-cost circulation algorithm on the surface does not appear to have any way to say, make it a maximum flow. Right? Because it doesn't demand a flow at all. So we need to do something to encourage the flow to go from S to T. And we want that encouragement to be very strong so that as much flow as possible will go from S to T. Now, given that we're talking about min-cost circulation, what form of an encouragement is available? Only prices, or costs, right? So what we do is we create an edge running from T to S, which has capacity infinite and cost minus infinite. Okay. And I claim that does the trick. How come? Yes?
The maximum flow, or the best cost circulation is always going to send just the most value across that edge because that's the only thing that matters. And that's going to be equivalent to sending the max flow throughout the rest of the graph.
Exactly, right? So since we've put an infinite negative cost here, it means that it's a gold mine to send flow from T to S. We're going to want to send as much as possible. And the only restriction is that if we're going to send flow from T to S, we have to balance that with an equal amount of flow going from S to T. And obviously, it's going to have to traverse other edges, right? So we want to send as much flow as possible from S to T so that we can send it back from T to S and profit, okay? And so that's going to cause us to send a max flow. Yes?
Will it not care about the cost anymore because we have minus infinity?
Well, so what's interesting is that it won't care. Well, physicists add infinities all the time, right? So yes, we've got finite cost in the rest of the graph, but we're going to want to minimize that cost as something that we add to the minus infinity, right? But let's do a more prosaic answer, a more sensible answer, because really you can't write infinities on things in your computer, right? I mean, you can never predict what's going to happen when you add nans and things. So we should instead replace this with some numbers that are as good as infinity, right? Some finite numbers. So what finite numbers will have the same effect as infinities on these edges? Let's start with the easier one. So if we want this graph to be finite, what capacity should we put onto the edge that will still allow us to make the argument we're making now?
Capacity or cost?
Let's start with capacity. Yeah?
The sum of all the capacity.
Good. So if we can upper bound the amount of flow that could go from S to T, then we can use that upper bound on the way back from T to S. And as we did in previous lectures, we can bound this by the total capacity of the graph, right? The sum of capacities of the edges. I'm going to be lazy and just bound it by m times the maximum capacity. Okay. Now, let me keep this small just so that it's clear. What sort of cost should we put onto this edge? Yes?
Minus m times the largest absolute cost.
Good. So you're asserting that it should be minus m times the largest absolute cost, which I will take as capital C. What's the argument for that? Let's think through that. Yes?
Should it be minus n times the sum of all the costs, so that you guarantee any path that you take from S to T is guaranteed to cover that cost?
Good. Well, so let's start with the argument and get to the quantity, right? So what's the argument for why there is some finite number that's going to work?
If there's a circulation that avoids TS, then we know that the total cost is less than the total cost is more than minus NFC. So circulation is F from TS really better.
Good. So that's the thing, right? If we look at the cost of sending this stuff from S to T, right, as long as it's more profitable to send it back, right, we just need the sending back to be more profitable than the sending, right? And then our algorithm will be motivated to use all of the possible paths. So really, the question comes down to how expensive can it be to send stuff from S to T, right? If we make it better than that to go from T to S, then we're done. So how expensive can it be to send stuff from S to T? Yeah?
Sum of all the positive costs?
Sum of all the positive costs, right? So that's where M times C would come from, right? Again, this is an upper bound on the sum of all the positive costs. I claim I can actually make a slightly better argument, okay? Because of what we just said, right? We talked about, we have these decomposition arguments, right? So how does flow go from S to T? It goes on paths, right? So if we upper bound the cost of a path, that will upper bound the cost of any of the flow traversal, right? So how do we need M times C to upper bound the cost of a path from S to T? Not really, because the path can only be n edges. So in fact, n plus 1, or n actually can only be n minus 1 edges. So nc is actually sufficient, because if we look at the decomposition of flow, each unit of flow is only costing nc to send forward, as long as less than nc to send forward. So as long as we get more than nc sending it back, we're fine. Okay? So these will serve as infinity for this problem, but are finite, and so we can now actually execute an algorithm. Right? And the other nice thing about it, looking forward to our scaling algorithms, is that we haven't changed the scale, right? Log of the maximum capacity has not noticeably changed if we introduce these additional, this additional capacity and cost. Okay? Whoops, wrong notes. Okay, so now we have shown how these two problems are completely equivalent. If I can solve one, I can solve the other in essentially the same time bounds. For insight, I'm going to give you one other different reduction. Another way of going from min cost flow to min cost circulation. Okay. And that's to use what we already have. So our goal is to find a min cost flow, but what we know how to do from previous lectures is find a max flow, right? So my step one for finding a min cost flow is going to be to find a max flow. And now I'm going to ask, what is it going to take me to get from some max flow, which might not be the min cost flow, and instead get the min cost flow? Okay. So let's suppose that we find some max flow f. Now, what we want is the min cost flow, which I'll call f star. What's the difference between them? And let's take that literally. Let's consider f star minus f. What is it? Yes. F star minus f is a circulation. How come?
Because the value is 0 from S to T, and then everything else is balanced. So the whole thing balanced.
Right. So the point is that you've got this flow which balances everything except at S and T. Right? It sends f units of flow from S to T. Well, now I take that and subtract a flow that sends f units of flow from S to T. Well, that means that I'm just sending f units of flow from T back to S. Right? So I have one flow of a certain amount from S to T, an equal amount of flow from T to S, so I get a total flow of 0 from S to T. In other words, S and T are balanced. And all of the other vertices are also balanced because they were balanced before. So I have something with balance everywhere, so I have a circulation. Okay. But is it feasible? Right? Feasibility is pretty important in what we've been studying. It's not feasible in our starting graph, right? I may have some negative valued, right? F may be bigger than f star on some edges and give me negative flow values. And so I have a feasibility problem. But I claim that this circulation is feasible in the residual graph of f. Okay. Because if you think about it, right, the residual graph of f is basically g minus f, right? So basically, if f star is feasible in g, then f star minus f is going to be feasible in g minus f. So let me fill in the details of that, right? So if f star on an edge E minus f on an edge E is positive, or is non-negative, right? What's that saying? That's saying I'm putting a non-negative amount of flow on edge E in the difference, right? So we have positive flow on E. But notice also that the amount of flow, f star E minus fe, is less than or equal to ue minus fe, right? Why is that? Well, because f star is feasible by definition, right? So f star E has to be less than or equal to ue. And so the amount of flow that I'm putting here is going to be f star E, which is less than or equal to ue minus fc, which is equal to the capacity of u of edge E in the residual graph, right? Now we just look at the other direction. If f star E minus fe is less than 0, okay, so that implies a negative flow on E, but we really didn't like talking about negative flows. So what is this really implying, or what is the meaning of this if f star E minus fe is less than 0? Yes?
Flow in the opposite direction.
Flow in the, right? A negative flow forward is a positive flow in the opposite direction, right? So this means a positive flow of f sub E minus f star sub E on the reverse direction. Okay, but if we're going to have a positive flow on the reverse direction, we better make sure we have capacity for it. So why would we know, why will there be capacity for this positive flow in the reverse direction? Sorry? Because we're looking at the residual graph. So what can we say about the residual graph? Right? GF has capacity F sub E on, right? This is the definition of the residual graph, right? Is that however much flow is going in the forward direction, you create capacity in the backward direction to represent removing that flow. So we have capacity of Fe, and we're only using Fe minus F star E on that edge. So we have a feasible circulation in the residual graph. Okay. Now, this does highlight an important point, which I will sort of state here as a detour. I mentioned how in max flow you can talk about the sort of net flow versus the net flow from U to V versus the flow on an edge, right? And it's funny, in previous classes I've always used just flow on an edge. In this class, because I tried to be consistent with a particular textbook, I went to using net flow. And that actually created some problems for one of your homework problems last week, which a few of you noticed, but many of you didn't. So I won't worry about that part. But it is not something we can do with min-cost flow. So why in min-cost flow do we need to think about flow on a specific edge instead of just the flow between two vertices? Is because in min-cost flow, it's actually quite natural to create parallel edges, right? So to ship stuff from here to Chicago, right? I can either send 50 pounds in a suitcase on an airplane, costing me $500, right? Or I can spend I can take 1,000 pounds in the trunk of my car and only spend $50 on gas, or I could have a few years ago. Or I can put 10,000 pounds into a freight train and only spend like $3 or something like that to get it shipped, right? So it's very natural in a min-cost flow problem to represent alternative paths between a pair of vertices, alternative ways of getting between a pair of vertices, which can have their own capacities and their own costs. And so it no longer makes sense to just talk about the amount of flow going between the endpoints, because you have to decide which edge you're going to use. And obviously, you're going to start by using the cheapest edge, and then when it's full, you use the next cheapest edge, and so forth. But this means you have to keep track of the flow on every edge. So for min-cost flow, we're really going to focus on this flow per edge perspective as opposed to net flow between vertices. Okay? Yes?
So one of the things that you mentioned was that per unit costs were constant on any of these edges.
Was that what were constant?
The per unit cost is constant for
Yes.
the first and the second unit.
That's right.
And this seems to let us use any sort of discrete function.
Yes.
Are we allowed
In fact, in a sense, pretty much everything that I'm teaching you works fine for a convex cost function. Okay? And this is sort of a discretization of a convex cost function. And working with convex cost functions makes everything more messy without really making it any more interesting. So we'll focus on just individual edges of fixed cost, but you can be aware that there is this generalization. Okay? So just notice that we're going to be talking about flow per edge, right? And this will be important for our analysis. But now we've completed this argument that the difference between the flow we found and the min-cost flow is a circulation, right? So let me box this detour. So now the cost of the circulation is equal to the cost of the flow that we found minus the cost of the min-cost flow, obviously, right? Because everything is linear. Okay. So coming back, remember, my goal here was to reduce from min-cost flow to min-cost circulation. So given that we have F, how do we find the min-cost circulation? Sorry, the min-cost flow. Yeah?
Find the min-cost circulation and residual pattern.
Good. So what we're going to do is find what we'll call Q, which is equal to the min-cost circulation in G sub F. And I claim that F star is just equal to F plus Q. So first you find any old flow in order to use up the capacity. Then you find a min-cost circulation and use that to shift to the actual min-cost flow by adding that circulation to the flow. So this provides a second method for solving min-cost flow by doing a min-cost circulation. Okay. Good. All right, actually, take a 2-minute break, even though it's late. The next question, again, we're following exactly the same path as we did for max flow. So the next question we're going to ask is about deciding optimality. So given a flow F, we can ask, is it a min-cost flow? And again, we're looking for easy mechanisms to prove that it is and that it isn't. Okay. So there's two pieces of this. Obviously, the first is min-cost flow by definition requires a max flow. But we already know how to find out whether something is a max flow or show that it's not. So we can take for granted that we have a max flow. And the question now is that max flow also a min-cost flow? Yes?
You can check by looking for any circulation that would generate profit.
Great. So the first claim is that F is a min-cost flow if and only if the min-cost circulation in GF has cost greater than or equal to 0. Anybody give the proof of that? Yes?
Or at least one direction. If it weren't, then you could just add in that circulation and you have a better one.
Exactly. That's what we proved right over here, right? If you find a min-cost circulation in this graph and its cost is less than 0, then you have just found a better flow, right? But that's not quite sorry, we can simplify it beyond that. Okay. So let's see, how do I want to say this? I'm trying to think if it's even possible for the min-cost circuit. Right. So you said the sort of it can't be less than 0. Can it be greater than 0? Can the min-cost circulation in a graph be greater than 0? This is another trick question. So assuming there are no lower bounds, what circulation is always feasible? 0 circulation. Then it has cost 0. So in fact, I can say this, right? So the min-cost circulation will never be positive. And if it's negative, as we just argued over there, then you can add it to the flow and get a better flow. So if you have a negative min-cost circulation in the residual graph, then F is not a min-cost flow, right? But what about the other direction? Right? So we want to argue that if the min-cost flow does have cost 0, then F must be a min-cost flow. But actually, before we go there, let's try and simplify this a little bit better. Sorry, simplify this a little further. So suppose that there is a negative min-cost circulation in G sub F. Can I find a simpler proof, right? Because we don't know how to find a min-cost circulation yet. So that would seem to make it hard to actually figure out whether our flow is optimal. So suppose that there is a negative min-cost circulation in GF. Is there something simpler we can point to that arises as a consequence? Well, we have decomposition, right? So let's take this negative min-cost circulation and decompose it into cycles. What can we conclude about these cycles, given that we are getting a decomposition from a negative valued min-cost circulation? Yes?
They're all negative or 0.
That they're all negative or 0 is too strong a statement. At least one is negative. Right, so the sum of all of the sum of this decomposition has to be negative, and so the only way that the sum can be negative is if there's at least one term in the sum that is negative. Okay? So if there is a negative flow, a negative circulation, then there's a negative cycle, right? And I claim that the reverse is also true, right? If there's a negative cycle, then there is a negative circulation, right? Why is that true? Yeah?
Take that cycle.
Just take that cycle, right? So we can put an if and only if here, right? So if F is not a min-cost flow, then there is a negative cost cycle in the graph. Okay. Now suppose that f is a min-cost flow. Can there be a negative cost cycle in the graph? So if there exists a negative cycle in G sub f, then I claim that f is not a min-cost flow. How come? Yeah?
And that cycles the flow, and then you get a...
Right. You can add it. You can add it to f to improve. Okay. So now we have our sort of key structural theorem, right? So we can conclude, we've now completed this, the proof of this claim, right? We can say more. So now we have this nice claim that f is a min-cost flow if and only if gf has no negative cycle. So we have we have a proposed mechanism for verifying that f is a min-cost flow. Of course, in order to actually implement that method, we need to be able to find a negative cycle in a graph that has one. Can we do that? Can we find a negative cycle if one exists? That may not be a problem that you've had to solve before. Or let me refine that. That may not be a problem that you solved before on purpose. But the existence of negative cycles was a problem that you may have had to deal with in the past as something that you didn't want, but that you still had to deal with. Yes?
The Bellman-Ford algorithm for shortest path.
So why do we use the Bellman-Ford algorithm for shortest path? Right? It's way worse than Dijkstra. Right? Dijkstra's algorithm is order m or so. Bellman-Ford is order mn. So why would we use Bellman-Ford? Yeah? Negative edges, right? Dijkstra's algorithm only works for positive edges. Right? Bellman-Ford works even if there are negative edges. Okay? So the Bellman-Ford algorithm for shortest paths, or the lesser-known Floyd-Warshall algorithm for shortest path, works even with negative edges, negative cost edges. But what does works mean? If you can have negative cost edges, then you can have negative cycles. What's going to be the shortest path in a graph with negative cycles? I see people know it by picture, right? This is the shortest path, right? If you have a negative cycle, then you can always get better by going around it again and again, right? So in fact, in graphs with negative cycles, shortest paths are not well defined. But Bellman-Ford discovers this. It discovers if shortest paths are not defined because of a negative cycle. And the way it discovers it also reveals the cycle. Okay, you'll see the edge length, the distance is going down and down and down, and you'll be able to detect in order mn time, here is a negative weight cycle. Okay? So that means that we now have an algorithm that can verify or check whether a given flow is a min-cost flow in order mn time, because that's what Bellman-Ford takes, right? So we now have order mn time verification of min-cost flow. So that's a nice first step. Okay. Now, in fact, it also suggests, in a very straightforward way, our first min-cost flow algorithm. Okay. Or actually, let me say min-cost circulation algorithm. Okay. Given what we've done so far, what is pretty much the naive and obvious way to find a min-cost circulation? Well, it's to creep up on it, right? If we don't have a min-cost circulation now and we can do something that makes our current solution cheaper, right, or extracts more profit from the network, then we should do it. So what procedure can we use in order to take a current circulation and make it into a cheaper circulation? Yes?
Look at the residual circulation.
So given our current F, let's consider GF. And what do we do with it? We want to make our circulation better. Well, the first step to that would be to decide that it's not already good, right? It's not yet a min-cost circulation. How do we check that it's not a min-cost circulation? Well, we look for a negative cost cycle in this residual graph. Once we have found that negative cost cycle, how can we make our circulation better? What we can do is send flow around that negative cost cycle. That has negative cost, so it extracts profit from the network for us. How much flow can we send around? We look at the minimum capacity edge on the cycle, and we send enough flow to saturate that edge. So we actually destroy that cycle, right? So we find a negative cycle, and we saturate it. So this is actually the first min-cost flow algorithm. It's by Klein, I think from maybe the 60s. It's called cycle canceling. Okay. How long is it going to take to find a min-cost circulation this way? Well, this is actually, if you think about it, this is the exact analog of the naive augmenting paths algorithm, right? Find any old path and saturate it. Now we are saying find any old negative cycle and saturate it. And the analysis runs much the same way, right? So each cycle, how do we measure progress? Well, we're looking at cost. So this drops the cost of F by at least 1, right? I'll again assume integer capacities and costs. Anytime I find a negative cycle, it drops the cost by 1. So how can I bound the total amount of work? I can bound it by asking what's the total cost drop that's possible from my start to my finish. So what is the range of possible costs for circulations? We actually already answered this question in a sense when we were looking at turning our infinities into finite numbers, right? We can bound the possible cost of the circulation by, well, it can't be less than minus MCU, right? If I saturate every negative edge, then the amount of money that will come out of the network is MCU. So that's the cheapest possible circulation. And the most expensive possible circulation saturates every positive edge, and so it has cost MCU. So that means that order MCU cancellations suffice. And we argued above that we can find a cycle to cancel in order mn time. So order m squared n cu time suffices to find a min-cost circulation. So we now have an actual algorithm with a running time. But it's not a very appealing running time, right? So this is, of course, a pseudo-polynomial algorithm. And on Wednesday, we'll develop the machinery necessary to get a polynomial time algorithm, and then and we'll discuss a little bit about strongly polynomial algorithms for min-cost circulation. See you then.